have the two circles. That's probably what the most like common thing you're used to seeing. There is in stats a outside square. And so sometimes whenever you are looking at two events, you find that there's people that don't fall into either category. So in the case of statistics, the sample space altogether is going to total up to 1. And so that is going to be the same thing as saying 100%. So what we kind of also have to take into consideration when we're doing these probability questions is that there are people who don't fall into either category. So this would be not A and not B. So I know that sometimes they ask you these questions and you're like, well, where am I supposed to get that information from? They will always give you enough to get to where you need to go. So if they want you to find the probability of not A and not B, they will give you everything that's kind of inside, and you just have to know in total, this whole thing equals to 1. So I take whatever I have, I subtract it from 1. Now, in the case of what we actually do with the two circles, we've already talked about ands and ors. The ors are unions, the ands are intersections. So an or statement is at least one event occurs. So I want you to kind of wrap your head around that, because in most cases, that seems like, yes, A, B, or A and B. However, there are some events, which we'll look at today, that contradict each other, that don't necessarily agree and say the exact same thing. And so a lot of people get confused and they'll say, well, you said to not do this, but now we're doing it because of this. Well, it's an or statement. The only thing that has to be true is one thing at a time. So just make yourself a little note. You can have contradicting statements. Contradicting events. We'll put it that way. And so the symbol for or is our little U. The and is both have to be true at the same time. Both events true at the same time. And so this is going to be our and statement. And what you'll notice, especially for Venn diagrams, the intersection is the and. So the place where they overlap is the and. Now, in the kind of events that we're going to do today, we're going to go through and we're going to talk about if I were to set up my Venn diagram and if I were to fill in all these values, which we will, what areas am I looking at for each particular situation? So in the case of the probability of A or B, so I'm going in symbol-wise, probability of A or B. So I'm going to kind of take this piece by piece. If I wanted to do the probability of A, that is going to be this entire circle. So all of circle A, because or is as long as one of them is true at the same time. So probability of A and then when I have the probability of B, that is the entire circle B. And so what you'll notice is in the nature of finding A or B, we already have the overlap shaded. So whenever you're trying to find an or statement and you've already set up your Venn diagram, you are adding the totals from A by itself, B by itself, and A and B. So this is what your Venn diagram would look like. For the other option, the probability of A and B, so or and, probability of A and B, the only time where both things are true together is that overlap section in the middle. where they intersect, which again is why the ands are called intersections. So we have A and B. These are the two most common probabilities that you'll be asked. Of course, the very basic and or. And then we kind of get into some of the weirder ones where there's like certain things they want to say no to, certain things they want to say yes to. But the next most popular one is going to be the one that symbolizes a complement. So in the case of our third example, the probability of A not happening. So there's a couple of ways we can write this. We can write it as A complement with the superscript C, but we also can go in and you can just use words. So I even hardly ever use the complement symbol. I just write not A. And that kind of conveys the only thing I'm interested in is everything but A. So remember, when I'm doing the complement, it's everything outside of what I'm trying to avoid. So what I'm trying to avoid currently is the circle A. So I am shading everything outside, including the outside sample space. So the most obvious thing that we're going to exclude is going to be B, because that is not A. And whenever you're doing not A, you don't want A to occur at all. So you'll notice I'm not shading the overlap because in the overlap, A is occurring. So not A is for sure B, but the part a lot of people forget about is the part where we have the outside sample space, because if you look to the very top of our page, we said that everything out here is not A and not B. So this is going to be a part of my not A sample probability. So again, if A is the entire circle A, I'm just going outside of that. Another way you can calculate this if you didn't want to use a Venn diagram is you can do 1 minus the probability of A. So again, the entire sample space adds up to 100%. So whole number 1, so I'm doing everything outside. Okay, the probability of A and B not happening together. So the only place that they happen together is the intersection, the overlap of the two circles. So that is the only place I'm trying to avoid. So in the left-hand side, I was trying to avoid the entire circle A. On the right-hand side, I'm just avoiding the overlap. So that means I'm going to include A, all of it, A that is not in the overlap. I'm going to include all of B that is not in the overlap. And then because I just want everything that is not A and B happening together, same thing that we did with not A. It includes all of the people that don't fall into either category. So I'm going to also shade my outside area. Now, I will say, again, it is not like a requirement for, oh, it made a circle. It is not a requirement for you to have a Venn diagram. Sometimes, and I will say rarely, do they ever ask you to make one on a test question because there are so many different approaches to answering these probabilities. So rarely do you have to make one. Sometimes in multiple choice, they will give you a Venn diagram and you have to be able to interpret it. But it still made another circle. Rude. I'm just gonna do this now. Boop. It has not done that all the last 3 classes I've taught this. sometimes it's beneficial just to see it visually, especially if you're one of the people who are visual learners who like to see what's going on. It's helpful to just have it there. Now, the best way, there's a couple of different ways you can write this. I think the most obvious way is A and B complement, but that is kind of the same thing as saying A complement and B complement have to happen together. And so whenever we do that, you could also write this as A complement and B complement. I will say, once you get to these weird ones where you're only excluding one small piece of the puzzle, a lot of people prefer to just nix writing it in symbols, and they'll just say the probability of A and B not happening together. And that is fine. Remember, College Board isn't necessarily going to require that you have to use symbols. They are completely okay with if you use words, but they do need some type of probability statement. So it doesn't have to be you're trying to figure out how to convey this using words and knots and complements and things like that. You can literally just give them a sentence explaining what are you looking for, and they'll give you credit for that. So do I have any questions on Venn diagrams so far? Sweet. Let's go to example 1. Now this is going to be one where we're actually going to use a Venn diagram to answer some questions. I went ahead and I organized the information in a table. They don't always give you the table. Sometimes this information is just in the paragraph, which you'll kind of see in your math lab today. But we're going to kind of take these numbers, we're going to put them into a Venn diagram. So we are looking at the taste preferences for 25 students. We're going to call event A sweet, and we're going to call event B salty. And we are going to go in and we're going to see where we're going to place these numbers. First things first, we have my best piece of advice for these types of things is I always put the overlap down first. So the overlap of these two things would be someone who likes sweet and salty food. So that means I'm going to put these 6 people in the middle. Now, I'm going to kind of show you an approach that will be helpful on your math lab because sometimes they don't tell you this is the number of people who only like sweet food. They'll say in total, there are 17 people who like sweet food. Well, if there's 17 people total and I already have 6 of them accounted for based on the overlap, that would mean that there would have to be 11 people in the sweet only category because this entire circle has to total to 17, which matches up with the fact that I have 11 people who are sweet only. Same idea. Sometimes the question will just tell you there are 13 people who like salty food. Well, if 6 of them are already accounted for, that means that 7 people are going to have to fall into the salty no sweet category. So I will say for sure on your math lab today, you're going to have questions where they don't separate it out for you. And sometimes they don't even tell you that they have not separated it out. My piece of advice, when any question gives you percentages, add them all up. And if it's over 100%, most likely they're in a situation where the overlap has been counted 2 times. And so you have to go in and figure out what would these individual values be without that overlap. So I have 24 people accounted for currently, which means that my 25th person didn't like either. They don't like salty food. They don't like sweet food. Maybe they like spicy or sour or something. But I will say having this organization is really, really helpful when you have to go on and answer a couple of different questions about whatever the topic is. So let's go in. Now, one thing I'm going to point out is this question asks us to find and interpret. Anytime you see the word interpret, there has to be a follow-up sentence. It doesn't have to be like you're rewriting like a novel. Basically, rewrite the question, include your value, you're good. But if it says interpret, you have to have something. You can't just have your number only. So first one, I'm going to go in and I'm going to go ahead and just change these to be in words, just so we kind of have a better idea of what's going on. So we are looking at the probability of sweet and salty. I'm going to try to remember what colors I've been using. Sweet and salty. So whenever I'm doing sweet and salty, where's my and located? In the middle. So I am interested only in this count here between A and B. Now, I gave you a Venn diagram. That's mostly for notes so that you can accompany it with the question and see like, okay, that's what we shaded for this. You don't have to have a Venn diagram in your answer. You can have one like that you're using overall if you'd like, but you don't have to write one out for every single question. So all I'm going to do is I'm going to take those 6 people that are in the overlap over 25, and that should give me 0.24. Now, I'm going to go in and write my sentence. The probability a student in class likes sweet and salty food is, now I included the word approximately. Technically, before I knew that you really didn't have to round any of these numbers. So because you didn't have to round, you really don't need the word approximately. So I'm just going to say 24%. If you did have to round, so say you are getting like a long decimal value, that's when we say that we are approximating it to be this. This was exactly 0.24, so you don't need it. If you include it, it's not wrong, so that's why I say better safe than sorry, but you didn't really need to round. I personally think that it's better to have percentages in sentences because it makes a little more sense, like if you were saying it out loud. So if you were to say the probability a student in class likes sweet and salty food is approximately 24%, that makes sense. But usually when you say like approximately 0.24, it doesn't roll off the tongue. So that's why I convert to a percentage. Now for my or, we have the probability of, we want sweet or salty. And we said that the or was going to be A by itself, so everything over here. A overlapped with B and all of B. So that means I am counting all 3 things from each of those areas. So I'm going to have my 7 plus 6 plus 11 all over 25, which is going to be 0.96. And that is going to be the probability a student in class likes sweet or, oops, forgot my word, likes sweet or salty food is approximately 96%. Now, if the question happens to give you the symbols, so what you're getting, you do have to, when you interpret the sentence, bring it back to the context of the question. You can't just say the probability of P, A, union B is approximately this. If they ask you to interpret, they want you to take it to the context of the question. So we have A or B. Now, for the probability of A and not B, again, I'm going to go in, especially for these, even I sometimes am like, okay, what am I looking for? A is sweet, and I'm just going to write not salty. So the people who like sweet food but don't like salty food are the people who fall into the category where it's A by itself. So we're basically going in and we're excluding that overlap of A and B. Now, the only people that fall into that category are the 11 out of 25, which is 0.44. The probability a student in class likes sweet And one thing that I will say, sometimes you can interchange and with but, and we'll have another way to interchange and in a second. I think sentence-wise, kind of rolling off the tongue, it makes more sense to say the probability a student in class likes sweet but not salty food is approximately 44%. Now, if you said and, it's not the end of the world. It makes the same sentence. It's claiming the same thing. It's finding the same probability. The only thing is you don't want to say or. For part D, we are going in the probability of, and this is an or statement, this is going to be not sweet or they like salty. So this is one where they're going to have contradictions. So I'm going to kind of take this in two parts. I'm going to first, and this isn't going to match the highlighting I've been doing so far, I'm going to highlight the not sweet. So everybody who doesn't like sweets is going to be out here. So this would satisfy the first part, the not sweet part. And then if I go in and I do the salty part, the salty part is everybody who falls into circle B. And so everybody who falls into circle B likes salty food. And I know there's going to be people who are like, but you highlighted the overlap, which has people that like sweet food. Yes, I did. Big thing to remember here is that this is an or statement. If you are doing an or statement, one or the other has to be true. They don't have to be true at the same time together. They just have to be true, one of them at that time. So yes, the overlap says that they like sweet food, but it's saying also that they like salty food, which is one of the things that I want. So we are going to go ahead and keep it as a part of our counts. So when I go in to find this, this is going to be the 6 in the middle, the 1 on the outside, the 7 that are salty only, all over 25. So the only thing that's being excluded is the 11 people who only like sweet food, and that's going to give me a sample or proportion of 0.56. So the probability a student in class does not like sweet food or like salty is approximately 56%. The only reason why I added in the word likes salty is because if I didn't, most people when they read that sentence, they would assume that I'm saying they do not like sweet food and they do not like salty food. So I'm trying to keep it so that it's still kind of matching the probability that I'm actually calculating. And for our second to last one, we have the probability, and this is going to be another or statement, the probability that it is going to be someone who likes salty food or, nope, sweet food. Sorry, switched it. I said salty so many times. They like sweet food or they like not salty. And again, this is an or statement, so only one thing has to be true at a time. So I'm going to go ahead and do the same thing I did before. All of my sweets are circle A. All of my not salty is everything outside of circle B. And so it's basically the same exact setup as what we did for part D. The only change is it's just flipped the part that we're interested in. So I am going to count everything except for the 7 that are salty only. So that is going to be my 11, my 1, and my 6 all over 25, which is 0.72. So the probability a student in class likes sweet food or does not like salty is approximately 72%. And I kind of set all of these examples up in the hopes that when you do get to your math lab and you see questions where they're asking you this and not that, you can come back and you can kind of look at these and be like, oh, this was the or, this was the and kind of match up these tiny Venn diagrams to what they're actually asking you to do. So always go back, check your notes, see if there's something there that could help you. Now, this one is going to be the probability of not A and not B. So I'm going in, probability, this is an and statement because it's an intersection. We want not sweet and we want not salty. Now, we've kind of talked about this one already on the front. This was that last shading that we did where it's everything outside. But just to kind of show you what this would be, if I wanted not sweet, that's everything outside of circle A. If I wanted not salty, that's everything outside of circle B. And so since both of these things have to be true, now don't shade in everything I'm going to shade because you're going to have to do erasing and I don't want you to have to erase colored pencil. This is everything outside of circle A. So that is satisfying the not sweet. This is everything outside, everything outside of circle B. And that is taking care of everything out here. But remember, you want in an and statement for both things to be true at the same time. So that means any place where they are not overlapped is not a part of my answer. So that means I'm erasing all of what is in circle A and what is in circle B because those were places where each one was true by itself. And in these cases of ands, both things have to be true together. And so I'm going to go in and the only thing I'm going to have is that one person out of 25 who did not fall into either category. So the probability a student in class dislikes sweet and salty food is approximately 4%. So Venn diagrams are not necessary, they're not required, but sometimes they're helpful, especially when you have a lot of information that you have to organize. It helps you kind of figure out where things have to go so that you can see, instead of looking at like all of these words, which is usually what messes people up, all of the words that they give you, you're focused only on, okay, what does it need to shade? What do I need to include? Any questions before we go on? Because it's going to switch gears a little bit before we get to the last two things. Okay, again, Venn diagrams, not necessary. You technically can still use the general addition rule and it would work. You technically can use a Venn diagram and it would work. You technically can look at it and kind of piece it in your head and figure out if this is there and that is there, this has to be the number, and it would work. The one thing that I always ask for your answer choices or your answers on FRQs is that you include those three things: a probability statement, your fraction setup. So where did you get to in the end? Because you should have some type of fraction that you got to, no matter what method you chose, or algebra if you did the formula, and then your final answer. I don't care if it's a decimal or a percentage. If it says interpret, make sure you have a sentence. Now, in the case of the multiplication rule, we're going to go into this very lightly and talk somewhat about conditional probabilities again, but we don't do like formal conditional probability until next week. So two events are independent if they do not influence one another. And the occurrence of one has no effect on the occurrence of the other. Basically, anything that is truly random, a dice, a spinner, what was my other thing? A coin, whether or not you're going to have a boy or a girl as a kid, 50-50 chances, those probabilities don't change. Anytime you have a theoretical probability that will not be altered over time, that is an independent event, which is why often when we're doing simulations, we use a coin, a dice, a spinner to pick things. Big thing here is if you are doing trials that do not fall into any of those categories, that they are done with replacement, meaning the probabilities don't change. I will say this, sometimes you'll have questions where they'll be like, 70% of Americans have a pet. And then they're like, you pick 5 people. What's the probability they all have a pet? Yes, we picked 5 people and they've come out of the population, but it's kind of like taking grains of sand away from a beach. Removing those 5 people isn't going to change the 70% probability of all US citizens. For the most part, it's going to stay 70%, even though I've pulled these 5 people out of the population. So in cases like that, where they give you like this known probability, as long as it's not like it's a known probability for 20 people in one class, you're probably not going to have something that's dependent because it's not going to change. Again, like grains of sand on a beach, taking one away isn't going to drastically change the composition of sand. So think about it like that when you have large populations. Now there is a rule, probability of A and B is going to be the probability of A times the probability of B. One little thing is this formula itself is not on the formula chart. Over time, as we use it, it's pretty obvious like what it's going to be. Like I need to multiply those 2 things together. But there is a way to kind of get it from one of the other formulas that they give you. It's just, we'll talk about that next class period because you don't know the formula yet and I don't want to take too long. So just know if you have ands, for the most part, you're multiplying no matter what. You will change it a little bit depending on if it's independent or not, but that's kind of what's happening. So in the case of our coin, so we are going to go in and what is the probability I flip a head and we're going to roll a 5. We're going to assume this is a 6-sided die. So I'm going to do the probability of a head and a 5. So if I have a 2-sided coin, that is a 1 out of 2 chance of getting a head. If I have a 6-sided die, that's a 1 out of 6 chance of getting a 5. Now I will say this. Don't get carried away. I have had questions like this pop up on other things like tests in the past and like on the AP exam. And people are like, a 5 out of 6. It's still a 1 out of 6 chance because it's one side of the 6-sided die. So we're going to go in, we're going to plug that into our calculator, 0.0833. And that, if I wanted to convert it to a percentage, is 8.33%. Remember, I don't care which place or which version you want to use as long as you either have a decimal or a percentage. So these 3 things, probability statement, your work, what are you calculating, and your answer is what you would need on an FRQ. Let's go on and let's look at what is the probability a mother will have 4 girls in a row. Technically, you could write girl and girl and girl and girl. But that is really, really not fun. So what I would probably write is probability 4 girls in a row. And it's still going to convey the same message. Now, if you're like, I like the symbols, I say it makes me write less words, wonderful, great, you can do that. Now, in the probability of having a girl, there is a 1 out of 2 chance that the first child is a girl. And because law of averages is not a thing, there's a 1 out of 2 chance the second, 1 out of 2 chance the third, and 1 out of 2 chance the fourth child is a girl. Now you can write it out fraction by fraction by fraction, but you can also write this as 1/2 to the power of 4 if you're repeating the same fraction again and again and again. So then I'm going to go in and I'm going to go ahead and calculate this 0.0625. Again, if I want to convert this to a percentage, 6.25%. Now, for example C, and notice that all of these probabilities are consistent. Like, yes, you had a girl. That does not change the probability of having a girl. Yes, you flipped a coin. Now, in the standard deck of 52 cards, we've discussed this last class period, but just to remind you, what is the probability I'm going to pull a red card and pull a black card? The thing to notice here is that they said you are replacing it and you are shuffling. That means you are getting the same random event again. Are you done, Tyler? No? Okay, just checking. So 52 cards in a deck. 13 of them fall into each suit, meaning half of them are black and half of them are red. So the probability of red is going to be 26 out of 52. The probability of black is going to be 26 out of 52. Now you also, if you knew that half of them are black and half of them are red, you could have used 1/2 and 1/2, and you're going to get the same exact answer. It's going to come all the way down to 0.25, which is 25%. And for our last one for dependent events, we have you're spinning a spinner 5 times and you want probability of 5 yellows. And I'm going to go ahead and say in a row because we want them to occur all together. You done? Yep. Thank you. So if I want them all to occur together, I'm going to take, there's 3 of the 8 wedges that are yellow. And I'm not going to write them 5 times. I'm just going to say I want to take this to the power of 5. So again, for dependent events, if you know those probabilities are not going to change, you can use an exponent to say this is how many times it's going to occur. So this is going to be 0.0074, which is going to be the same thing. If I wanted to, I could write it as 0.74%. Now, this is going to be a small disclaimer that really has nothing to do with this. I mean, it does, but it doesn't. If you're going in, and I'm going to write it down here, only because we got a small decimal on this last one. Sometimes when you're calculating values like this, the possibility of it occurring is really, really low. And so when you go to your calculator and you do something really small, like 1 out of 10,000 or something like that, your calculator most likely is giving you something like 5.2387, and it's going to say e to the -4. And you may have seen this on one of your math lab assignments, and you type in your answer because you know you did everything right, and then it's like, no, try again, or whatever it says to you. I think it says try again. The first thing that should be a red flag in this case is all probabilities have to be between 0 and 1. So if you look at this and you're like typing in 5.23, you've already messed up because you cannot have a probability bigger than 1. What this notation is telling you is that you need to go in and you need to move the decimal 4 to the left. So that means this number is actually 0.0005238.7. Now, MathLab does not ever ask you for that many decimal places, but it asks you typically for 3 or 4. So this may be 0.001 if it's 3, or 0.005 if it's 4. So just keep that in mind. Double check if you're certain that you're doing everything correct and MathLab is still telling you that it's wrong. Most likely, it may be something that falls into this category where you haven't actually written the correct decimal down. It happens more than you think. Okay, last piece of information, and this will go quick. We have two events are dependent if they influence one another. If I could influence, bless you, one another, that means the occurrence of one changes the occurrence of the other. So this is going to be trials without replacement. So the probability of A and B is equal to the probability of A, still going to be multiplication, times the probability of B, but B is going to turn into a conditional statement. So this conditional statement, we're going to define down here. That means the probability of B given A has already occurred. So think more, because given is going to be what this bar is representing. Think more in line of, I have a room full of 100 people and it's 60 men and 40 women, and I take one person and it's a woman and I don't put her back. That's going to change the overall probability of how many women are in the room. Now, if I'm looking at all United States people and I have 60% are men, 40% are women, and I take one person out, most likely the probability is still 60-40, even though you removed that one person. So think of the sample, the scope of how many people you're actually looking at. So let's go in and let's try a couple of these. It's going to work exactly the same way. I have the probability of a standard deck of 52 cards. What is the probability of pulling a spade and pulling a 5? Now here's where I'm going to make a disclaimer, because I should have worded this a little bit differently. We're going to assume the first card that was pulled is not a 5. We will kind of approach the situation where it is a 5 next class period. But for now, we're just going to assume the first one is not a 5. So in a deck, there are 13 cards that are spades out of 52. I'm taking that out. I'm not replacing it. And if they don't say that they are, that's usually the assumption. If you're dealing cards out, you're not dealing it and then taking it back. You're dealing it and dealing it and dealing it. So in this case, if I wanted to pick a 5, there's 4 5s in the deck. However, one card has been removed, so it's no longer over 52. It's going to be over 51. And so if I plug that into my calculator, it's 0.0196, which is the same thing as 1.96%. So the only thing you have to kind of evaluate, because you treat the questions exactly the same, is you have to determine, am I putting things back or am I keeping them out? Because then that's going to change that second fraction. We have the probability of pulling a jack and then another jack. So the probability of jack and jack. So there are 4 jacks in a deck of cards. Yes, the same exact thing. If I pull one card out, that's going to reduce the denominator by 1. But you also have to think, if you're pulling the same card out in a row, that's also going to decrease the numerator. So the numerator is now going to be 3 out of 51. And so that's going to be 0.0045, which is 45%, 0.45%. And just to take this all the way back to our first example, because again, it's not always like cards and coins. Sometimes it's people. We want to find the probability. It's the same exact prompt as before, that you select someone who likes salty food and then select another person who likes salty food. So that means I'm going in and doing the probability of salty and salty. So salty food is, there are 13 people total. So 13 out of 25. And then if I select another person, that means I'm going to drop the denominator to 24. But because that person already selected has liked salty food, I'm also going to drop the numerator to 12, which is 0.26. which is 26%. And our last one. What is the probability you select someone who does not like sweet food and then select a person who likes sweet food? So I'm just going to say not sweet, and then we want a sweet. I also, just to convey, then is equal to and. I know and has a lot of meanings in probability, but that's basically saying two things have to happen together. For not sweet, that is going to be my 8 people here. So 8 out of 25. And then for sweet, that is going to be the 17 people here. But again, I'm still dropping that denominator down to 24. Thank you. And so in the end, we get 0.2267, 22.67%. And that will be my last thing. Now, you will have a math lab